So welcome to this lecture on policy-based reinforcement learning. I want to start actually this few videos with a small citation that I came up with. And this is actually by Vladimir Vapnik. Many of you may know them from his work on support vector machines. And he at some point said, "Never solve a more general problem as an intermediate step." And so far in reinforcement learning, if you remember correctly, we started all over again where we initially in the first lecture said, okay, our new goal is actually to find a policy that maximizes the expected return. And if you consider Vapnik's rule above, actually you might want to ask yourself, if we care about an optimal behavior or if we want to find an optimal policy, why don't we actually learn the policy directly? So why do I say this? You might also remember this kind of sheet that I put up in the first lecture where I actually defined a little bit what we will be talking about in this lecture. And what we so far did is actually we concentrated mostly on the left part in here. The right part is actually up to the second half of the lecture. And so far, if we're working on experience data, what we actually did is we learned a value function, and from that value function, we derived a policy. And in this value function learning, actually so far, we somehow always did a kind of dynamic programming, as we found a setting of linear equations, a large setting of linear equations that are all satisfied. And if we have this set of linear equations and they are satisfied, we actually have the optimal value function, and from that we could derive a policy that actually defines the optimal behavior. However, this was an indirect way, because actually what we are interested in was the policy and not the value function in the first place. We somehow, through the Bellman equations and through the iterative Bellman updates, we always did the indirect way of actually calculating our policy. But there's actually a second thing, or actually a second branch that we can actually deal with, also using experience data to learn a policy, and this is actually what we will be doing in this lecture. So in this lecture we will be talking about learning a policy directly, which we will be doing using policy gradients, and of course we will also leverage all the things we already learned in value-based reinforcement learning, as there is also methods in between that help learning a policy while leveraging information about a value function. So these two different kinds of deriving or coming up with a policy, either value-based reinforcement learning or policy-based reinforcement learning, they are different in many areas. They are different conceptually both and also empirically. What you will see is that in policy optimization, we actually optimize what we really care about. While in dynamic programming, all the optimization was indirect, as we really tried to exploit the problem structure. We tried to set up a self-consistent system of linear equations. So that's the conceptual difference, but there's also an empirical difference. So what you will see is that policy search or policy optimization in general is more compatible with rich architectures we know from deep learning that also include something like recurrent neural networks. What you will also see during the implementation of the exercises, you will see that you can implement policy optimization algorithms with only a few lines, and so actually what you have seen is Q-learning and SARS were also in few lines, but when we actually came up with all the value function approximation, where we really tried to make them applicable to large state spaces, we really had to apply many tricks to actually keep that thing stably working. But what you see in policy optimization is general that you can come up with very few lines of code and also use neural networks to actually optimize the policy directly. There is also one empirical thing that also we will discuss in this lecture, and this is about sample efficiency. So you will see that value-based reinforcement learning in general is more sample efficient, because you actually can reuse sample experiences through a replay buffer, which is usually which requires actually more tuning for policy optimization algorithms. But however, what you will see also in the implementation during the exercises is that you can actually, if you want to set up something that works quickly, policy optimization algorithms are much easier to set up and get them to work. Okay, so let it formalize maybe a little bit. So in value-based reinforcement learning, what we actually did throughout the last 4 or 5 lectures was actually that we approximated parametric value functions. That could either be a state value function or a state action value function, so V or Q, using some parameters of a neural network, for instance. And if we actually had this, we could actually generate a policy, maybe a greedy or an epsilon greedy policy from that value function. So what we actually had is we had the environment and our agent on the top in here. And this was some kind of indirect, so the environment provides a reward and the state action next state tuple to us. And using the next state, we actually evaluated our value function, and using the value function, we actually had a policy extracted that actually lets us help derive and execute an action in the environment. So our goal was actually, or formal goal was actually to find good parameters W that approximate the true Q function. So this was actually our goal in the last lecture. And what we now do is we make it more direct. So in this lesson, actually, we will directly parameterize the policy. So we don't want to actually get this indirect way, but for estimating a value function and then extracting a policy from it, we directly want to parameterize the policy. And we want to parameterize the policy as we'll see it in a minute. It could be stochastic or deterministic policies, but actually we want to find parameters theta for a policy pi that actually maximize the long-term reward. So we still have a policy that gives us an action depending on a state and a set of parameters theta from which we can draw actually an action that we can execute in the environment. One thing also to mention, we will still focus on model-free reinforcement learning. We will only get back to the model-based versions when we actually talk about model-based reinforcement learning in the upcoming lectures. Okay. Okay, let's maybe put what I just said a little bit more in a pro and con list actually. Because actually, in contrast to Vapnik's rule that we actually had introduced in the beginning, there is actually also reasons to consider other viable objectives depending on your actual problem that you want to solve. So there is a lot of work actually that considers model-based reinforcement learning, which is actually the left part, which we will deal about in the upcoming lectures. Model-based reinforcement learning, in a sense, it's not a bad thing actually to do, because actually what we want to do in model-based reinforcement learning, we want to draw experience samples from the environment and we want to learn a model from it. And if we have a model from it, actually we can use this model for planning. And in a sense, it's easy to learn a model from data. Easy, not meaning that actually it's everyone can do it or it's easy to do it. It's just well understood because it's a supervised learning problem, and we can leverage all the latest research from the supervised learning literature and apply it into our setting. So we can actually draw samples from the environment and learn the dynamics that actually capture everything that you need to know from the environment. So if you do this, actually you're shooting not too low. So you actually try to learn everything from the environment. A real world example would be, for example, you just play Atari, for instance, and you first learn a model, a forward model from the environment that actually predicts. There's different versions also to do this, but in the simplest cases, it takes a state and an action as an input and actually predicts what the next state would look like. So if you do something like this, you do not actually need to execute the action in the environment, because you can use your model actually to predict what's going to happen if you would execute this action. If you can do this, you can actually apply planning algorithms that actually execute in simulation what's going to happen, and then you can optimize over this. Planning is still hard, but you can actually learn the model. However, now there arises the question, what if the background actually changes of your environment? Then actually your forward model is completely rubbish, so you can actually throw it away and learn a new model. So this is actually what I mean with objective, that the objective that you're actually doing captures irrelevant information. So actually, if you play, for instance, the game of Breakout or some other computer games, there is a lot in the environment that you actually see that's not really relevant for your agent or the reward function or also the dynamics of the environment. So you capture a lot of irrelevant information that you also learn, and from a computational point of view, you may focus also computations and capacity of your neural networks models towards predicting these irrelevant details, which in turn means that you lose accuracy and precision on the things you really care about. And the thing is, or why is this? Because during the learning of the model, you are not really informed about the final objective. So you do supervised learning on your model dynamics, but actually your model does not actually know what you want to do with that model afterwards. And because of this, you actually cannot do any better in this case. And still, so while learning the model is actually something that's easy or well understood in this case, computing the policy, so through planning through your model, is still a non-trivial problem that can also be computationally expensive, but we will focus a lot on this on the model-based reinforcement learning lecture. Okay, so then the other side of the coin was value-based reinforcement learning. So value-based reinforcement learning, in comparison to model-based reinforcement learning, is really closer to our true objective, actually. So we only care about the things that really matter in terms of their relevance to us, so their reward, actually. So we exploit the Markov structure of the underlying problem and we try to learn this one. It's really simple so it's fairly well understood, actually. So everything that we actually introduced in the last 2 or 3 lectures, you could leverage all the information that you know from previous machine learning or deep learning lectures, because it was somehow similar to a regression target. So we actually had a neural network, and the input to the neural network was some state or action, and you know what we have talked about. And we had a regression target. So we actually tried to predict a real valued number that actually describes or actually approximates the value function. So it's fairly well understood. However, actually it's not like regression in general, because we have this bootstrapping issue. So we actually we use our neural network or our predictor actually to also generate the targets we are optimizing towards. And we've seen that through the so-called deadly triad, that to stabilize such a learning framework might be challenging in practice. So actually what we have seen is that we can actually use it. However, it's still not the true objective. So our true objective was actually to find a policy that maximizes our return. And while we could actually, if we have found the optimal value function, we actually would achieve our goal. However, imagine that, for instance, you have a very bumpy road, and you want to find a policy that actually goes over this road. And imagine that the optimal policy would just mean accelerate. In every situation, just accelerate. So it might be intuitively very easy to actually find an optimal policy that always drives forward. This could first either be easy to learn, and second, it's also easy to represent it. So we do not even need to take the observation into account. So, however, we don't know this. But actually, so the policy is really simple, and it can also be expressed using simple models. However, the value function could look very complex, because actually you have different friction on the ground and different gradients going over them. So actually calculate the value function seems really complex, and it seems also quite unrealistic that you really approximate the true value function through limited experience in this case. So you would actually, in value-based reinforcement learning, you require much richer function approximators to actually capture the details of the value function that you actually need to extract your policy from the value functions. We also have seen further problems, meaning that if we approximate the state value function, we do not really capture the dynamics, so we actually would need to compute a further Bellman backup. While the queue actually needs captures this one-step look ahead in the dynamics. So actually, we do not need to actually know the probability transition matrix for the next steps. However, there's also two limitations with that, which we actually did not really cover in the lecture so far. The first one is that actually we need to actually sample more to actually also cope with every action, every state, which is a minor issue. But the more really limitation is in this case that we require a discrete state space. So we actually had, if you remember in the DQN example, we had a regression head per action that we could actually use. So we actually calculated for a limited number of actions that we can take their Q function. And in many situations, we have a continuous action space. So we also introduced the continuous state space, which was one motivation to actually use function approximation. But in many real-world problems, we also have continuous action spaces. And it's not that easy to just put continuous action spaces in our DQN. However, we will see this in upcoming lectures. So this is actually where policy-based reinforcement learning has much, much more advantages in it. Yeah, so actually, finally, policy-based reinforcement learning. Policy-based RL actually seems to fit with Vapnik's rule. So we actually want to learn the policy directly because we're actually interested in optimizing the long-term reward, which is actually driven by our policy. It's actually the right objective and is what you want. However, on the other side, it also ignores that there's other learnable knowledge in our environment. So it actually might be a good idea to capture some relevant information in the environment that's not really directly related to our policy, but that might help during policy learning. So, for instance, you could think about that your input might be an RGB image, and in this case, you just process your convolutional layers in a neural network to actually predict the action. And in the beginning, you really see a lot of your embedding space or your representation after the convolutional layers is not really converged yet. So in the beginning, you actually learn a lot about the environment, but you do not learn a lot about your Q function or your policy first. You actually learn how to extract features from the environment. And I mean, you could actually use CNNs and learn filters. Using data you get somewhere in the environment to actually get a good representation that you can then use actually for policy learning. We will also see in this case in here where we actually introduce actor-critic algorithms, where we can also make intermediate use of value functions. So we actually learn a policy in combination with a value function and combine the advantages of both approaches in this setting. Okay, so to round this up, what's the differences between value-based and policy-based reinforcement learning? We have value-based value functions on the right side and policy functions on the value functions on the left side and policy functions on the right side. And value-based RL learns a value function and extracts an implicit policy using, for instance, epsilon greedy. In policy-based RL, we actually have no value function. There's no values. We do not talk about values in this case. And we learn a policy directly, while we also, in the end of this lecture, define a method in between that are called actor-critic, which actually learn a value function and a policy in combination. In this case, the actor is actually the policy, and the critic is actually some baseline that actually introduces a value function in a sense. And we actually combine them together to actually outperform simple policy-based or simple value function-based approaches. Okay, so advantages of policy-based reinforcement learning. I think that's the last slide to actually motivate from a general point of view. We will see actually in policy-based RL, we have good convergence properties. So you will see that while we actually had a lot to tune, also we had a lot of hyperparameters in the value function-based RL, we do not actually need to tune so much in policy-based RL. But however, the second, maybe most weighting advantage is actually that we can easily extend policy-based RL, policy-based policy optimization to high-dimensional or even continuous state and action spaces, so both state and action spaces. We can learn stochastic policies, which is something I will introduce in the upcoming slides, which is one of the underrated problems that we will see in practice. And we have seen that sometimes policies can be very simple, while value functions or models might be very complex in practice. Which means that we have a rich domain we need to approximate, but the optimal policy would always go left. There is also some disadvantages that we will also discuss in this lecture. Policy-based are less susceptible to local optima, especially when we use nonlinear function approximators. We will also see methods to actually, or we will see algorithms that actually try to cope a little bit with this. A second disadvantage might also be that the obtained knowledge is very specific and does not really generalize well, meaning that if something little in our environment changes a bit, like we have other agents or we unlock a door or something like this, in general the policy is rendered useless. So it might be very hard to completely switch to something else. It's not useless, but you really need to care about how to recover from such changes in the environment, or if there is something changing in the environment. And this is also relating to the next point. We ignore a lot of information in the data when we use that in isolation. So actually what you will see is that we will draw samples from the environment. So we will run in trajectories and we will draw the samples from the environment, and then we learn from them and then we throw them away. It might also be advantages not only to train a policy, but also train something like a model or something like a value function with the data you also get from the environment. Okay, let's talk about stochastic policies. So in the past lectures I always said that there's like deterministic and stochastic policies, but we didn't really care so much about stochastic policies so far. So far actually what we have seen is we have seen actually deterministic policies like this. So we had a Q function, and our state gives the Q as, so we actually put in our neural network our state input, and we get all the state action values from them, and then we selected the action that actually maximizes the regression heads in here. So we actually took the argmax of the Q function, and this is actually the action that we could take. So our policy was just parameterized by a state and a set of parameters. Instead, what we did not yet really considered so far were stochastic policies, where we actually define a probability distribution over a state space, and this is actually our policy. So in this case, for instance, we could describe our policy as a probability distribution over the available states given our parameters theta, and then we would actually sample from that probability distribution an action that we can actually take from the environment. So in this case, we actually got a deterministic action from it because we had applied this argmax operation. In this case, we define parameters for a probability distribution. In the easiest case, it would be like a normal distribution or a Gaussian, defined by a mean and a variance. And from that Gaussian, or for multimodal Gaussian, we actually sample an action from. So this is actually something that first allows for continuous action, but also allows to actually solve problems in practice that we did not yet really cover so much. And I will introduce the advantage of stochastic policies in a nice intuitive example in the upcoming slides. So consider maybe one simple problem that's you play rock paper scissors with an opponent. I mean, I think rock paper scissors is not so difficult as blackjack, where we had in the beginning. So the rules are really simple. So we have a 2-player game, and the rules are simple: scissors beats paper, rock beats scissors, and paper beats rock. And you make something like click, clack, look, and then you select one of these. And your opponent also selects one of these, and actually what you want to maximize is actually the total reward, meaning that the winnings over the sequence that you actually play. And now consider policies that iterate such rock, paper, scissors, and you learn from that data. And now imagine that you actually sample experiences from the data, and you would actually learn a deterministic policy. It might be a greedy, or sometimes even an epsilon greedy policy. And just imagine this. What would happen if you actually learn a policy and then you apply a deterministic policy in a sense? What would happen? Exactly. So your opponent would actually easily see that you follow a biased or some policy, and it can easily exploit this policy because actually you draw your samples through some, I don't know, through some deterministic function, and this is actually something that could be estimated by your opponent, and he can then simply exploit this knowledge that he actually sees, and would actually win the game. So in this case, you can actually formally prove, if you want, we will not do this in this lecture, that a uniform random policy is actually the optimal policy due to a Nash equilibrium. You can actually look in this from the game theory point of view. But you actually can only win or make a draw if you really follow a uniform random policy. This is one sense. This is why you actually need a stochastic policy that describes a probability distribution over your states. Okay, this is more like an intuitive example. Let's consider a more example that we're used to in the reinforcement learning so far. Let's talk about grid worlds, because we love grid worlds so much. What we really did not really focus so much in the so far was actually partially observable Markov decision processes in a sense, which is something that you will see a lot in practice. So you often are faced with partial observable Markov decision processes that you actually try to overcome using state augmentation, which we talked about in the last lecture. But in general, you cannot formally be sure that your MDP is really an MDP and not a POMDP. And this is a nice example to actually visualize this. So imagine that you have an agent and you start in one of these 5 cells in here. You have no memory or something, and you just get aliased information about your state space. And now we consider, actually, we define our state space like this, that we just have a 4 tuple in here describing north, east, south, and west. And we actually, if there is a 1, that means actually there is a wall to the north of us, there is a wall to the east of us, there is a wall to the south of us, and there is a wall to the west of us. And this is actually how we encode our actions. So we actually go east, north, east, south, or west. And what you will see, what you might also want to have, would have seen through this example, the problem is that if you are in one of these 2 states, you cannot really differentiate those states, because in those states, actually, there is no wall to the left and the right. And there's, in both of these states, there is a wall to the north and the south of the states. And now the question is, the reward of, you might also have guessed, that you get a minus, so the episode ends in here and here and in here, you get a minus reward in here, and you get a +1 reward if you get to the treasure. And now the question is, compare deterministic and stochastic policies in a sense. So in this case, value-based reinforcement learning learns a near deterministic policy, because you actually, over the argmax, select you select a deterministic action in a state, and depending on greedy policy and epsilon greedy, so you can actually relax the problematic issue a little bit with epsilon greedy. However, if you select a greedy action in this case, what you actually will do is that under the state aliasing, your optimal deterministic policy will either go left in both of these states or go right in both of these states, because you actually cannot. Because you put this state information in your neural network or in your Q table and you select the argmax operation, and this is either left or right because they are actually encoded the same way. In this case, of course, you will go right, here you will go down, and here you will go left, because actually you can't differentiate those states. But however, what this means is, depending actually where you start, you might traverse the corridor for a very long time, actually, or like infinitely long. So if you start right, everything is fine, you go to the treasure. If you start left, everything will be bad, and you will be trapped forever in this environment. Now, instead, consider what would happen if we would describe our policy not by a deterministic function, but by a stochastic process actually. So in this case, an optimal stochastic policy would look like this. So we would still like have a very, put our mean in order to actually sample the action right in here, down in here, and left in here. But we would actually be able to describe that in these states, we actually have a 50% chance of going left and a 50% chance of going right. If we set up this policy, this policy will actually maximize the return if we put it, if we throw an agent into this grid world. And this also means that with a very high probability, we will reach the goal state even in a few steps. So we might take the wrong way, but we will immediately go back and then actually transit through the corridor. So actually, if you are in here, you would go left, and even if then you would by chance define right, you will go left again, and then you will maybe go by chance by left. So epsilon greedy, in some sense, would also help in this setting, because actually with a certain amount of probability, you would select not the greedy action in this case. However, what you also have seen is that at some point you want to converge to a policy, and then you want to run your policy with a greedy policy. So it's anything but a guarantee that epsilon greedy will find a good solution to your problem. And also one more thing to say at this point, while this seems very simplistic and unrealistic, maybe in the first sense, there is many real-world examples out there that are really actually POMDPs instead of MDPs, and they really have such problems. You will not really see them like that specifically in practice, but you will feel it because you actually optimize your state space, and value function-based methods will simply not work so well, while policy-based reinforcement learning will actually exploit such things. Yeah, so another example would also, I read it, I don't know where I read it actually, but another example is also poker. What you actually want is, you want to do an unpredictable bluff at some points, and what you actually want to, so you want to be this bluff, you want this bluff to be stochastic in nature, so you do not want to be predictable and deterministic, because if you would like do a deterministic bluff when a state looks like this, this would be seen by your opponents, and they would then also know that you're bluffing, and they would react accordingly to this. Okay, so policy-based reinforcement learning can learn such optimal stochastic policies, and we will see how to actually do this. Okay, so, but now the question is, how could we actually deal with this, and why is this actually working in practice? So, what we would actually do is, our policy, so in this sense, I think now we are accompanied with neural networks so far. So what would this actually mean? So we have seen card pull in the very first lecture, which was the simple environment where you have to steer a card and actually to balance a pole at the top. And card pull is defined by the position of the card, the velocity of the card, the angle of the pole, and the angular velocity at the tip in the top. And in this simple example, where I will also provide a Twitter notebook from this, but you will also implement this, what you could easily do, you can actually learn function parameters theta that define an action over your elements in your state space. In this example, so what you could either do is, or what you could like do, this would be something like a linear case, but what you also could do is like you put your state space into a neural network, you apply nonlinear operations on it, and at some point you will output an action that actually does balance and control the pole. And to do this has also another advantage if you do this. So just imagine what you did in the beginning. So if you want to balance the pole, and you would, for each of the states, calculate a value function, and you would actually now think about think about what happens during your policy updates in training. So what you actually do is, if you update your parameters, you want to actually what you actually do is you update your parameters to be in the greedy policy improvement step. What you actually do is you take a policy and you made a greedy step over to your value function. So you actually exploit your value function and you're being greedy towards it. Meaning that in this case, you might see a small change in your Q function, which is because actually you apply smooth updates towards it. We have seen this. We have a learning rate. We do stochastic gradient descent. We apply smooth updates to our value functions. However, no one says actually that these small changes that we apply to our Q function does not lead to large changes in our policy. So with a small change in our Q function, this might actually give us a totally new policy, meaning that through our policy updates or value function updates, this could lead to a very unstable process and we see large jumps in our policy. This is also something that you might see with value function approximation TQNs. You will see a lot of variance in this. So potentially, I mean, you can cope with it using smaller learning rates, but in general, while you only smooth the updates in your Q function, you cannot be sure that the updates in your policy are also smooth. This is something that you can change. So there's a potential that early Q function lead to completely different policies in the next sampling of the next trajectory. But what we actually would do, so this is actually something that we will talk a lot in the upcoming slides, we want to update our parameters a little bit in the direction to actually increase the return. So there's no Q function in between. And what we actually want to do is this would actually, in a sense, lead to small changes in both the Q function and the policy, because we actually parameterize the policy parameters directly. So as we apply small updates to our policy, we can also be sure that the policy actually didn't change that much and we do not see such large jumps in the policy. And this also leads to a much more stable learning process because we actually see small updates in the policy. This is something that many algorithms also try to more explicitly constrain. So we actually see that by design, we also already see that applying gradient descent to the policy parameters directly guarantees small changes to the policy. However, we will see also in more advanced algorithms that it is very important to actually make these policy updates smooth and we can constrain them even more. And this is something that we see. However, what's a little bit unclear at this point might be the case is how can we actually calculate the gradient in this step? So I talk about that we want to update our policy parameters. And the thing is, so in the carpole example in the previous slide in here, you have seen that we want to, given a state space or state parameters in here, in the input layer and the output layer, how can we actually form the derivative of this function with respect, how can we actually derive the derivative of the return with respect to the policy parameters, which is something that's not that clear. So actually, how can we define the gradient of our policy? This is something that we will do a lot in the next lecture. At this point is, what we actually want to have is, we want to define the gradient of our policy with respect to the return that we actually get. So we want to increase the policy parameters so we want to change the policy parameters such that the expected return with our parameters is actually ascending. So we want to maximize the expected return. And we will see how to derive this in a minute. So what we have seen is learning the policy directly is much more straightforward and is actually the direct thing we can do. But the question arises, how can we actually calculate the gradient term in here? And before we actually think about how to analytically derive this gradient, we can also shoot at this problem with a much more simple idea. So actually what we could do is we just run our policy, and for each parameters we actually what we actually want to do, we want to evaluate the gradient for each dimension, and this is just meaning that we can estimate the kth partial derivative of our objective function with respect to the policy parameters by just perturbing this policy parameters a small amount, epsilon, in the dimension, and then we can get the partial derivative of this parameter. So what you would actually do is you have a policy that's parameterized by some number of parameters, so it's in total it's k parameters, and what you do is you run a bunch of episodes, and then you change the case parameter a little bit, and then you run a bunch of episodes again, and then you see actually how much different your policy is actually. And if you do this for each of the parameters and you sample a lot of trajectories, you can get an estimate actually of the gradient of the partial derivative of your objective function with respect to the policy parameter. And this is actually a simple optimization algorithm called finite difference stochastic approximation, and this is also sometimes in our reinforcement learning literature called finite difference gradient estimator, because you have a finite difference and you estimate the gradient for each of the parameters. You also see a variation of this from control literature where it is called simultaneously perturbation stochastic approximation, because through perturbation you approximate the gradient in a sense. It's simple, however it's noisy and it's inefficient, but it's sometimes really effective, and there's also successes with it. Because you also, in the next slide, you will see an example where this actually works. However, you see that it's very inefficient because you need to run a lot of episodes to actually do the estimate of the gradient. And if you estimate the gradient, you do an update of your policy, and then you need to run over it again. While it is noisy and inefficient, however, it works for arbitrary policies, even if the policies are not neural networks and they are not differentiable. So because you actually just perturb the parameter, you can get an estimate of the gradient without actually deriving your parameters with respect to your objective function. So this has actually applied successfully in practice. So you see here IBO. IBO is this small robot, and there is this is some time ago, it's like almost 20 years now. And the idea was within the Robocop to actually take this small IBO and to actually apply or learn walking patterns. And you need to learn fast walking patterns, of course, and the speed decides either of if you win or if you lose. So in this setting, what they actually did is they parameterized the policy as an ellipsoid in here. So this is actually the one of the legs, and you can actually define a policy through 12 parameters. And in this case, what they did is they run many episodes and let IBO run through a parameterization of this policy, and they applied FDSA. And then actually evaluate each of the policies by the field traversal time. And what you see, this is an early iteration in this, where you actually see IBO running or walking actually. And if you do this, you actually estimate or perturb many of the parameters, and then you run them and average all the returns. And at some point you see that IBO is running much faster. So you actually see that through just sampling the gradient through perturbation of your parameters, you can actually come up with a policy that's pretty well working in the end. However, what I also told you about, a problem of FDSA in practice is that it requires a lot of samples and trajectories from the environment to actually get a precise or accurate gradient estimate that you can use to actually improve your policy and to go over again. And also, what's really problematic in practice, depending on how much you actually perturb the parameters, at some points you have also stochasticity in the environment. So things always, things like if you apply an action in a certain state, this might lead not always to the exact same next state, because it also depends on some varying parameters in the environment. So in stochastic environment, and you have a small c, it is really hard to distinguish between a positive and negative return in this case. So you really need to sample a lot of trajectories to actually get a low variance estimate of the result of such a perturbation. However, there's also a building on top of this ideas. There's also another idea which is called Augmented random search, which is a famous algorithm that was introduced, I think, 2 or 3 years ago. And augmented random search basically builds on basic random search that I will show you on this slide. And the idea is actually that you pick a policy pi theta, and also in the beginning that we also, as we did it before, we perturb the parameters by applying a positive and a negative constant times the delta, where v in this case is something lower than 1, which is a constant noise, and delta is a random number that we sample from a normal distribution. So this is actually, like in FDSA, we also perturb the parameters. And then actually what we do is we run the policy and apply actions based on the positively perturbed parameters and the negatively perturbed parameters. And then we also collect the rewards that we get through this perturbation. And what we then do is actually, for all of our deltas, we compute the average. We compute the average rewards that we get. And then we update our parameters theta using this average and the learning rate alpha. So this is actually what we do is we have a positive and a negative perturbation, and depending on what happens actually, we take the average over these parameters and then we update our parameters towards this. However, this works well in practice, so you can actually do this, and it is an improvement over FDSA. However, you have three main limitations that are actually then improved by augmented random search. The first thing is, as the iterations go on, the difference between this one and this one, they can vary significantly depending on, so if you have a positive perturbation on the parameters and a negative perturbation of your parameters, so you actually steer them in both directions, the difference here can vary significantly. And this might also lead to, if you have a static alpha in this case, so over the iteration, this can vary a lot. And alpha is then not really a constant learning rate in a sense. So this is like shooting very high at through some iteration and very low through certain other iterations. And because of this, what one improvement is that you actually divide the rewards in here by their standard deviation. That actually allows you to use a static alpha in this case. So what you also see is that you have different, so your states actually that serve as an input to your network or to your estimator, they have a different range of actually being defined. So in carpool, for instance, the the position of the card ranges from -5 to 4.8 to +4.8, while the angle is in radial basis, meaning that it's ranging from -0.2 until 0.2, meaning that actually the weight on the state input of for the position actually weighs implicitly more than that of the angle, because actually the value range is smaller. Actually meaning that you have to normalize the state depending on their range actually. So you equally well adjust what's happening with the rewards in here. And another thing is, what you also see is, if you do n of these rollouts, some of these rollouts and perturbations have a really poor performance, and they really push the average down a lot. And what they did actually, they sort all the rollouts in a decreasing number and only select the best k runs to actually compute the average to do the update. So this is like the simple idea of augmented random search. You can also put this in a pseudocode in here. Don't be too crazy about it. There's different versions they put in a single algorithm, but we will get through this shortly. So in the beginning, what we actually do is we sample a bunch of deltas that we actually define how many these are. So we sample n different deltas to actually generate variations of our policy parameters. What we then do is we actually run 2 times n simulation of rollouts, actually with a negative perturbation and the positive perturbation of the delta terms actually. So we have n different policies, and we run them with a positive variation and a negative variation. There is now the V2 version where we actually divide the input states and we standardize actually the state space, because we actually divide them by their we actually subtract the mean and divide them by the variance. And this is actually what we do in here and estimate in here. And what we do here is this is the thing where we only select the top k entries to actually form the average. And at a point we then do actually the update step of our policy, in this case, where we do the average over the positive and negative reverse differences of our different policy variations. Yeah, so actually seems very simplistic and straightforward, but actually works very well in practice. So it's actually, now I have the paper presentation in here. It's a NIPS publication from 2018, so it's like 3 years old, and it actually produces state-of-the-art results on classical random over classical random search methods, and also on well-known control environments that we also use in deep RL algorithms. What you see here is you see the performance that it actually works and results in a reasonable reward in most of the Muchoco environments that you see here. Yeah, so while it is comparable in the performance to modern deep RL algorithms, what you see is that actually there is not that much hyperparameters that in this case we actually need to configure. So we need to define how many policy variations we want to produce, and we need to define alpha, but they are not so important in their variations actually. So what you see is like there is less tuning in this, and we have seen that in deep RL actually we require a lot more tuning of our algorithms. You also see like movies from this. So this is like half cheetah. It's a cheetah with it's only the half of the cheetah, and it cannot like fall to the side. It just needs to learn to run forwards. And at the beginning, you see nothing is working. After 100 iterations, even you can see that the thing is moving forwards, not like going to the ground. And if you run this thing for 300 iterations, you see some pretty well result already. Although it might get a little bit better in the end still. But you can actually also, after 300 iterations of this simple algorithm, come up with a policy that actually leads to this behavior. Yeah, so what is actually the pros and the cons of methods such as augmented random search? Yeah, it's simple to understand and also simple to implement. I mean, the real-world implementation using Python or C++ is not much more than what we have seen in the pseudocode. And you can also throw away all the V1 versions. You can just implement V2T, and this is then a bunch of lines of code. You have not that much parameters that you actually need to tune, and they are also very robust, so that you can, like, we have a default setting and it works reasonably well. And it's like embarrassingly easy to parallelize, so you can like come up with a setting of different deltas, and you can like really just process them in parallel on your CPUs to collect data. However, there's also some cons in this, so you actually tend to favor lucky rollout. So if you like by chance got a reasonable result, this will have an influence on your selection, many. Also, like what we have seen in the other random search methods, there are stochastic environments, and in stochastic environments it's not always easy to distinguish if your change in the rewards is actually due to the parameter variation or due to the noise in the environment. You do not exploit the sequential structure of the problem, so this just runs. So all these things we saw in augmented random search, there is no really sequential thing that we actually exploit in our problem. We just optimize our policy and look if it's better or not. It's like a black box optimization in a sense. And what you also see in practice is that you will require 10 times more samples approximately compared to a properly tuned deep reinforcement learning algorithm. Okay, so this was the intro to policy-based reinforcement learning. At a sense, we did not really talk about policy-based reinforcement learning algorithms so far or what's behind them. And sorry for the long introduction on that. So we just needed, I think it was interesting, or it was very important to cover the basics from random search, actually to cover the problem of policy-based RL. But in the next lecture, we will really talk about deep reinforcement learning, and we will really see that we can actually do very good in this.